Google has spent years trying to push past the fundamental limits of transformer architecture, and with its recent models, it may have just finally achieved the one breakthrough every AGI roadmap has been waiting for, which is a model that can finally remember and grow and adapt as it runs in real time.
What makes this development genuinely groundbreaking is how, if you have ever tried to make a large language model reason over an entire code base, or a long legal case, or weeks of system logs, you already know the frustration where you stretch the context window and stack prompts and costs rise with every extra token, and still the model loses track of something important, right? When you need it most. Why transformers are extraordinary short term thinkers that are masters at pattern matching and structure and immediate reasoning, but as long term storage systems, they are brittle and expensive and fundamentally limited, where the deeper the context, the more they struggle, and the memory problem never really goes away. How that pressure is exactly what pushed Google to develop something radically different called TITANS, which at first glance might look like just another name in the growing forest of transformer replacements. But when you examine it closely, it stops feeling like a variant and starts feeling like a shift in philosophy. And the reason Titans is built on a simple idea of letting attention handle the present while letting a dedicated neural system become the memory of the past, where instead of forcing everything through attention, Titans splits the job cleanly, with one part of the model handling short-range reasoning and the other becoming a long-term memory that learns while the model is running. Once you understand why underneath this architecture sits a theoretical foundation called Mirus, which reframes nearly every modern sequence model, including transformers and RetNet and Mamba and RWKV and Titans, under a single unifying perspective, where in the Mirus view, these architectures are not wildly different inventions, but variations of the same underlying mechanism. How this long-term memory is not a single vector or compressed state or crude summary, but a deep, multi-layer perceptron whose weights serve as the memory itself, where the model receives tokens and generates key value pairs, and the long-term memory tries to predict those values from their keys, with the difference between prediction and reality becoming the surprise signal, and what it means that in needle in a haystack scenarios Titans maintains extremely high accuracy even when context stretches far beyond typical transformer limits, performing well beyond 16,000 tokens and scaling to context exceeding 2 million tokens in some experiments, while in the Babylon benchmark, which demands reasoning across widely separated facts, Titans outperforms larger models like GPT-4 and Llama 3.170 billion, and even Llama 3 equipped with retrieval augmentation, all achieved with Titans models containing as few as 760 million parameters. You'll realize this isn't about replacing transformers, but complementing them by giving models a memory system that transformers never had, offering a way to stop wrestling with long context limits and replace brittle retrieval setups with learned memory, while treating memory as a design choice rather than an afterthought. Something extraordinary just happened in artificial intelligence architecture research that could fundamentally reshape how we think about long-term memory in neural networks, and the implications go far beyond what initial technical papers suggest. Google has spent years systematically trying to push past the fundamental limits of transformer architecture, and with its recent models, it may have just finally achieved the one breakthrough that every AGI roadmap has been waiting for. A model that can finally remember, grow, and adapt as it runs in real time without requiring massive context windows or external retrieval systems. If you have ever tried to make a large language model reason over an entire code base, analyze a long legal case spanning hundreds of pages, or process weeks of system logs, you already know the frustration intimately. You stretch the context window as far as the architecture allows. You stack prompts carefully. The computational costs rise dramatically with every extra token you add, and still, the model loses track of something critically important right when you need it most. It's a fundamental limitation that has plagued the field. Transformers are extraordinary short-term thinkers. They are absolute masters at pattern matching, at understanding structure, at immediate reasoning over local context. But as long-term storage systems, they are brittle, prohibitively expensive at scale, and fundamentally limited by architecture. The deeper the context you need, the more they struggle. And the memory problem never really goes away, no matter how cleverly you prompt. That pressure is exactly what pushed Google to develop something radically different from standard approaches. At first glance, Google Titans might look like just another name in the growing forest of transformer replacements and alternatives that researchers have been exploring. But when you examine it closely and understand what's happening under the hood, it stops feeling like a variant and starts feeling like a genuine shift in architectural philosophy. Titans is built on a deceptively simple idea: let attention handle the present moment, and let a dedicated neural system become the memory of the past. Instead of forcing everything through attention mechanisms that get increasingly expensive, Titan splits the job cleanly. One part of the model handles short-range reasoning over immediate context. The other becomes a long-term memory system that actively learns while the model is running. Underneath this architecture sits a theoretical foundation called Mirus. It reframes nearly every modern sequence model that researchers have developed. Transformers, RetNet, Mamba, RWKV, Titans, all of them under a single unifying theoretical perspective. In the Mirus view, these architectures are not wildly different inventions created from scratch. They are variations of the same underlying mechanism. Each is an associative memory system that maps keys to values, updated through some internal objective function, and stabilized through a form of controlled forgetting. When described this way, all the mystery and confusion disappears. The field becomes a design space with clear parameters you can turn and adjust. Titans embraces this perspective completely. It pairs a compact attention core with a neural long-term memory system. This long-term memory is not a single vector. It's not a compressed state. It's not a crude summary of what came before. It is a deep, multi-layer perceptron whose weights themselves serve as the memory. The model receives tokens, generates key value pairs from them, and the long-term memory tries to predict those values from their keys. The difference between the prediction and reality becomes what researchers call the surprise signal. This surprise is the gradient the memory uses to update itself at test time, meaning while the model is actually running. A small surprise means the memory already understands this pattern from previous tokens. A large surprise means the model has encountered something new or structurally important that needs to be stored. This is what gets encoded into the weights. The process is actually quite intuitive when you think about it. If you're processing text that repeats familiar patterns the model has seen before, the memory barely changes. If you suddenly reach a critical new concept or an unusual detail that matters, the memory reacts and updates itself. The long-term memory becomes a kind of distilled notebook, evolving with the sequence, absorbing only what matters and ignoring repetitive noise. Over long stretches of data, millions of tokens in some experiments, the memory becomes an abstract representation of the global structure, not a literal log of every single token. That is the crucial difference from Transformers. Titans doesn't try to remember everything. It tries to remember the right things. Mirus formalizes this by breaking down a sequence model into 4 critical decisions. You choose a memory architecture, which could be a vector, a matrix, or a deep network. You choose an attentional bias, a rule that determines what the memory prioritizes internally. You choose a retention gate, a form of controlled forgetting that ensures new information doesn't overwrite everything that came before. And finally, you choose a memory learning algorithm, a method for updating the memory through online optimization. Once you describe models this way, the entire field becomes coherent and understandable. Transformers use a shallow memory with dot product bias. RetNet uses a decaying kernel. Mamba uses a fixed-size recurrent state. Titans picks a deep memory with online gradient descent and explicit retention mechanisms. They are all solving the same fundamental problem with different architectural choices. The researchers behind Mirus pushed these ideas further by exploring variants that use different objectives. They built Monada, which uses stricter generalized norms for memory updates. They built Yard, which relies on Huber-style losses that make the model less sensitive to outliers in the sequence. And they built Mara, which frames memory as a probability distribution enforcing stability through constraints rather than decay. The specifics vary across these implementations, but the message is clear. Attentional bias is a design parameter, not a fixed rule of nature. Memory can be built in many different ways depending on what you optimize for. The test-time learning mechanism inside Titans can sound alarming at first. It suggests a model that is mutating its own weights while running, which sounds unstable. But Titans only updates the long-term memory in a carefully controlled manner. For each token, it produces a key and value, feeds the key into the memory, and observes how wrong the prediction is. That wrongness is the surprise signal. High surprise triggers a stronger update to the weights. Low surprise produces almost no change. The memory then takes a gradient step toward encoding the association. The update includes momentum, which keeps the memory sensitive across multiple tokens whenever a conceptual shift occurs. and the retention gate gently pulls the weights toward stability, preventing drift and allowing unimportant details to fade naturally. This retention gate is more than a convenience feature. It is an essential part of safety and stability. Without controlled forgetting, early sequence models would spiral into instability or fill their capacity with noise. TITANS solves this by letting repeated patterns win and letting rare, irrelevant patterns disappear. Forgetting becomes a controlled feature that protects the model from stale associations and sharpens long-term recall. It also makes long-session interactions more consistent because the model's internal state doesn't depend on every quirk of the prompt history. To understand TITANS in context, it helps to compare it to its architectural neighbors. Transformers store a growing key-value cache. This is powerful but becomes prohibitively expensive as sequences lengthen, with costs rising quadratically. Linear recurrent models maintain a fixed-size memory, which is efficient but compresses information into a tight bottleneck that eventually loses detail. TITANS sits between these extremes. It keeps the precision of local attention while pushing long-range storage into a deep memory that can learn abstractions. It allows fixed memory cost while unlocking long-range expressiveness. For tasks that stretch across millions of tokens like multi-document reasoning, genomics, time series modeling, or long-running agents, this hybrid structure becomes very appealing. TITANS ships in three forms, each connecting memory to the main stack differently. The MAC variant, or memory as context, provides a global summary vector at each step, allowing attention to decide when to look at nearby tokens and when to look at global context. It works naturally for extreme long context question answering or retrieval augmented generation. The MAG variant, or memory as gate, uses the memory to control the behavior of sliding window attention. It widens or narrows the receptive field depending on what the memory believes is relevant. This variant excels in workloads like log analysis or long code traces, where local structure dominates but global jumps occasionally matter. And the MAL variant, or memory as layer, treats the memory as an interleaved layer, alternating between local computation and global recall. It resembles a standard deep model and behaves like a general-purpose long-context engine. Benchmarks make the case clearer. TITANS matches or surpasses strong transformer and linear recurrent baselines on C4 and Wikitext while preserving training parallelism and linear inference speed. But the more impressive results come from long-context stress tests. In needle-in-a-haystack scenarios, TITANS maintains extremely high accuracy even when the context stretches far beyond typical transformer limits. It performs well beyond 16,000 tokens and scales to context exceeding 2 million tokens in some experiments. In the Babylon benchmark, which demands reasoning across widely separated facts, TITANS outperforms larger models like GPT-4, Llama 3.170b, and even Llama 3 equipped with retrieval augmentation. All of this is achieved with TITANS models containing as few as 760 million parameters. These results are no accident. Ablation studies show that the depth of the memory network matters enormously. When you compare two memories with the same parameter count, the deeper one consistently wins. It achieves lower perplexity, better long-range recall, and more stable scaling as sequence length increases. Depth gives the memory representational richness that shallow memories cannot match. The question many people ask is whether TITANS signals the end of the transformer era. The honest answer is no. Transformers solved short-range reasoning so well that they will remain central to machine learning for years. TITANS doesn't replace the transformer. It complements it by giving models a memory system that transformers never had. It offers a way to stop wrestling with long context limits, to replace brittle retrieval setups with learned memory, and to treat memory as a design choice rather than an afterthought. For anyone building real products, the key question is straightforward. Where does your workload require stable structure across hundreds of thousands or millions of tokens? Where do you currently rely on window hacks, vector databases, or sharding tricks simply because your model can't remember what you gave it earlier? Those are the places where TITANS becomes transformative. Its combination of test-time learning, disciplined forgetting, and deep memory abstraction provides a roadmap rather than a series of patches. Google's direction is clear from the research.
The future of AI may depend less on making attention mechanisms larger and more on fundamentally rethinking what memory should be in neural networks. And judging by the direction of research, from TITANS to Mirus to the many emerging memory-centric architectures, we're witnessing a genuine shift. That's it for today, folks. See you in the next video.